guys, this is Lab 5, Magnetic Braking with Faraday's Law. My name is Landon Hicks. Let's get into it. Alright, introduction and background. The purpose is to observe how Faraday's Law is acting on the magnet. We're going to compare ideal models in glow script with in-person experiments. And we're going to look at our system and surrounding. Our system is our falling magnet. Our surroundings is everything else. Alright, necessary principles. Alright, so Faraday's Law and Lenz's Law. This is how we're going to calculate our EMF. This is going to give us our potential difference that is then going to be divided by the resistance to get our current that is creating our magnetic flux. Or not creating a magnetic flux. That is created by the magnetic flux and therefore creates the magnetic force that's on the magnet and therefore slowing down the free fall. Newton's law is how we're going to observe this free fall. We're going to look at its acceleration due to the net force. And Beer's law is how we're going to look at our magnetic field at any point. Magnetic dipoles, the magnetic force outputted by, or the magnetic field outputted by that induced current acts as a magnetic dipole, and so we're going to look at how that affects the dipole that is falling, which is the bar magnet. And magnetic force is calculated by what we calculate in Beer's law and in Faraday's law, and how we're going to see the force that is going to determine our acceleration. Alright. Lab procedure. We're going to mark the north pole of the magnet using a magnometer, and then we're going to hold the tube vertically, measure that. We're going to drop that magnet down the tube and record it, make sure it's in the frame of the camera. We're going to repeat this 5 times. In my lab, the time to fall was 1.876 seconds, and here's some more experimental data. The aluminum foil was 0.28 meters, the inner radius was 0.016 meters, the outer radius 0.038 meters, and the resistivity was 2.65 times 10 to the negative 8th. The bar magnet had a mass of 0.016 kilograms and a mu calculated from lab 3 of 1.12 amperes per meter squared, or times meter squared. Alright, so check my questions. Why can't we use a Ferris tube? So a Ferris tube is a steel-like tube, and they would have a significantly stronger impact on the magnet. It would have so much so that it would slow it too much for us to really have a cool experiment. It wouldn't look at like free fall at all. It might even completely stop it for a time being. And it wouldn't be as easy to analyze. This is a paramagnetic material, aluminum is, and this would allow it for a significantly weaker force on it that still looks like a fall. Alright, so what happens to the magnet? How does this compare to the magnet falling in free space? So magnetic force is equal, it makes the net force lower. When the net force is lower, this is going to result in a lower A, right? So F divided by M equals A. Well, if our F net is lower, then our A will also be lower. And therefore, our normal free fall speed of our acceleration of 9.81 meters per second squared would be dropped down to something between 0 and G. So, glow script model. We got our constants, the length of our tube and all that. And then we go into calculating some of the magnetic field, the bar magnet, and the magnetic flux. We just do this through defining. Let's see. So, and then we're going to calculate the magnetic field, calculate the magnetic flux. We do this through the Faraday's law equation and through Beer's law. So gravitational force, that's already given for us. Calculate the magnetic force from the tube and the magnet. We do that through whatever we found in steps 2 and 3, and it will give us the current, and then we can use what we know about dipoles to calculate the net force, and the net force can then be plotted onto our velocity time graph that we're going to get through the results of the model. Alright, so let's look. We get this graph, and so the most important thing on this graph is the acceleration. So we're going to see for like the first 5/100ths of a second, it's almost directly downward, and this is basically a slope of negative 9.8 meters per second squared. And that's going to be when it's basically in free fall. When you see it go upwards, that's when the magnetic force is actually greater than the gravitational force because the acceleration is upward, meaning the net force had to have been positive. And then it levels out. When it levels out, this means that F is 0, and A is therefore 0, and therefore the forces are equal to each other and cancel each other out. And once it slopes back down, that's when it's going to exit the tube and resume free fall. So interpreting the simulation, the EMF and forces produced. The color of the rings indicates the current created. The blue is clockwise and the red is counterclockwise. The orientation creates a magnetic field that opposes its motion. If we were to flip the poles of the magnet and re-drop it, the currents would reorient to oppose the fall. So say if we were to flip the magnet, it would have a red on top and a blue on bottom, right? So, how can we make the lab better? Alright, there's an infinite amount of small circles that can be on the bar, and mine only shows the 2 closest rings on there that are the complete loops that are creating this EMF, or that the EMF creates a current. And these are going to be the most impactful, and they're why the ones that we're analyzing, but technically there is ones along the entire length of the tube. I could put those, and that would make the lab better. How did the forces balance through the fall? As you can see, I said this in the graph. It's based on the acceleration. If the acceleration was essentially negative 9.81, there was no magnetic force. If they were equal, the 2 forces were also equal. If it was a positive slope, the magnetic force was greater than the gravitational force, and when it then resumed, there was no longer magnetic force. So the discussion. Times first models were about the same. So in person, 1.876 seconds, and then the other one, it differed by about 3 thou. Forces on the magnet, there's 2 forces, magnetic and gravitational. So possible source of error. Time is measured by humans, making reaction time factor, and non-uniform foil. As the foil kind of scrunched up, I'm sure it was used in a couple labs, and this could maybe affect the thickness of the area, and the area is a factor in the magnetic flux. So that changing would be an inconsistency. That was not the computational model. So what if the resistivity was reduced as close to possible 0? How that affects the dynamics? So the current would be exponentially larger, right, because it's the EMF divided by the resistance, right? So resistivity would affect the resistance, and therefore with 0 it would have a very, very large current, making the magnetic force incredibly high, making maybe a much, much slower falling time. What if holes or slats were cut in the tube? How would this affect the ring currents in the model? Well, the ring currents need to be closed, and this would make them unclosed. Right, so at these points it would fall closer to free fall because the force would be disrupted. Right, so we wouldn't have this complete rings of current that are then causing this opposition to changing magnetic flux. All right, thank you.